this on our test, okay? So please don't freak out about when you see the formulas today, okay? It's not something to freak out about. This is a, hey, we're gonna learn this, and it's a nice to know kind of thing. And it was a good thing to put on a Wednesday because it's pretty short, okay? I could hardly find homework problems on it. That's how obscure it is, okay? I found 2 homework problems in WebAssign, and then the other 2 problems are on what we did yesterday, okay? So it's just, I want to make sure we've covered every topic for you guys. You guys are heading that direction where we've got almost everything covered, so I want to make sure you've got it, okay? Oh, David says it's raining. The music worked. Cool. I can't see out my window right now, so I'll have to go look in a few minutes. I can't hear it yet. So the gardener came, and I wasn't expecting him today because I expect he normally comes in the afternoon, so I was expecting him after the rain. All right, so the focus of this topic will be to investigate how close our Taylor approximations are to the actual value of the function. So remember yesterday we were talking about that we can take this polynomial and use it to estimate like sine and cosine and e, transcendental things that we would normally have to put in the calculator, we can estimate with a polynomial. That was our big kind of discovery yesterday. But the question remains, because mathematicians are never just satisfied with, hey, that's a good estimate, is exactly how good of an estimate is that, okay? There's a lot of different names for the same thing, okay? So we often use the words remainder and error interchangeably. So you'll see the word remainder, you're going to see the word error for this. So the remainder of a Taylor polynomial is basically the exact value we call f, right? Our polynomial is the p, and then the remainder is whatever's left over. So basically it's like what's beyond what they asked us to calculate. If we're 3rd degree, what's 4th degree? That's the remainder, okay? The remainder will serve as the error in our approximation. So basically our error is the absolute value of the remainder, or the value of the original function minus the value of the polynomial, okay? The theorem below gives the general procedure for estimating the remainder associated with a Taylor polynomial. So there's 3 different names for this thing, okay? The theorem, often called Taylor's theorem, defines a remainder that when isolated is referred to as the Lagrange form of the remainder or the Lagrange error bound. So lots of different names for this one single thing, okay? If you want to read about good old Lagrange, there's some information here, okay? I'm not going to read it today. So Taylor's formula, Lagrange error bound. If a function f is differentiable through the order n plus 1, meaning beyond where they asked us for, okay, in an interval I containing c, then for each x and I there exists a z, so there's this weird z that comes in, that's between x and c such that. So basically what they're saying is they're going to give us the original x value, they're going to give us a c value, somewhere in between there, there's another value. Okay, that makes sense, right? Intermediate value theorem would say, hey, there's something in between there, right? This is the polynomial part, okay? This is the remainder. Okay, so that was the Taylor's theorem part. To find the remainder, okay, and there's another version of it down here in this Taylor's inequality thing. We have to take one term beyond, okay? We find the maximum value of that one term beyond. That's going to make more sense in a minute, okay? And then we divide by the factorial of one term beyond. And this looks like what we were doing yesterday, right? X minus c, so there's our piece of our Taylor polynomial, but we go one beyond what we have. So notice there's an x in here or an n there. If we had a 3, we would evaluate it 4 for our remainder. And notice it's all absolute value, okay? This thing here got totally, I'll fix up tip here in a second. Let's talk about the inequality and then I'll talk about the tip because that's going to lead into example 1. So we can often represent the error as a bound using the inequality. So the remainder is less than or equal to the maximum that's of the function, the value of the function evaluated one beyond. Okay, the maximum that could be. Okay, we'll talk about a little bit more about that in a few seconds. And then the n plus 1 times the n. So it's the same formula, really. The notation max of the f to the n plus 1 of z represents the largest value And remember, this is representing a derivative. So it's like third derivative, fourth derivative, fifth derivative evaluated at z, will take on for a z that will typically lie between c and x. Okay. All right, let's fix this up over here. This was supposed, I don't know what happened. It was supposed to say sine of x or cosine of x, not sun x. I have no clue what was going on. I don't know why it either didn't copy and paste well or I typed it wrong. I have no clue. So let's talk about sine and cosine. And I know we're not the best graphers of sine and cosine because I just kind of skimmed over it when we were teaching. It was like the one thing I cut out and trig for you guys. We did a little bit. So we know that sine and cosine do this like wavy thing, right? When we're doing that wavy thing, what's the biggest number that we can get? Does anybody know? Anybody remember? What's the biggest number sine can get? If I'm not doing period and amplitude and all that extra stuff, think unit circle. And some of you are there. It's 1, right? What's the smallest that it can get? Okay, and remember, you know, I know you're paying attention because you're helping me out in the chat. So if I'm thinking about the absolute value of those numbers, so I'm thinking about the absolute value of those numbers, there's no way that sine or cosine is ever going to be bigger than 1 or smaller than -1, meaning the absolute value of that is it's always going to be 1. That is its max. I'd say probably about 80% of the time when we do these problems, it's going to be a sine or a cosine. So our max is going to be 1. Is that, it really isn't either one. I didn't do a very good job. Sine actually starts at 0. Sine looks more like this. It was more of a cosine than it was a sine. Cosine starts at 1, but I wasn't very symmetric about my origin. All right, I noticed, hi Luis and David, I noticed you guys popped in. How are you doing, Missy? Good. Ellie got super excited today. She got a sweatshirt from her auntie that was from her favorite YouTuber. So. All right, I'm sad that I have a child old enough to have a favorite YouTuber. So she becomes a teenager in like a few weeks, like a month and a half. It's very sad. All right. Okay, it's not a gamer YouTuber, so it's not as bad. That's fine. That time flies. It does. It does have a cartoon dinosaur on it. It does. All right. Let's keep going. Okay. Are you done for the day already? Oh, okay. Did you do your math work? Okay. Go work on help Andy find some lunch. Okay. Good. All right. So let's talk about what we've got here. So example 1 says, determining the accuracy of an approximation. The third Maclaurin polynomial for sine x. So they were nice. In this problem, they gave us the polynomial. We didn't have to calculate it. So third degree Taylor polynomial is x minus x cubed over 3 factorial. We learned about that. We learned about that yesterday. Okay. So it wants me to use Taylor's theorem to approximate sine of 0.1 by the third degree Taylor polynomial. And then here's the kicker. This is why we need Lagrange, because now we have to determine the accuracy. So that's where Lagrange pops in. Okay. So the first thing I'm going to do is the first sentence. Use Taylor's theorem to approximate. Okay, so let's do that. So we have, I'm on the wrong spot here. The sine of 0.1 is approximately, and I'm going to plug into this polynomial that they gave me. 0.1 minus 0.1 cubed over 3 factorial. So I'm going to go for the decimal point. You could use the fractions, I guess, but I think the decimal probably makes more sense in this case. I'm going to go ahead and type that into Desmos. Let me get rid of what's there, just so that you understand what I'm doing. So 0.1, and you believe my answer. And it was 0.1 to the third divided by 3 factorial. Oh, 3 factorial. There we go. So 0.998333333333333. Okay, so 0.09, I missed a 0. 0.98998. I totally keep messing it up. 33333, whatever. Okay. All right, now we're going to find the remainder. Okay. The 10th is next week, Samuel. This week started on Monday was the 1st, and when you add 6 to that, that becomes 7, right? So we're still not at a week. All right. Then we're going to do the remainder piece. So my remainder, and we want the remainder for the 3rd degree polynomial. So this is just notation, remainder of the 3rd, because I have to figure out how good of an approximation I got. So remember, we're going to put in the max value we can get of 1. Okay, so if I'm in 3, tell me in the chat, what's 1 beyond? What's 1 beyond 3? So what derivative am I really looking at, or what term am I looking at? All right, so 4. So the 4th, I want the max of the 4th derivative could be evaluated at x divided by 4 factorial times, and then I'm going to put the estimate in there. So instead of writing x, we put 0.1, which was the value they wanted us to put in, to the 4th. Okay, we just talked about this. No matter what direction I go with sine or cosine, what's the biggest that number can get? Can you guys tell me in the chat? We had a little discussion about that. So what's the biggest that sine or cosine can ever get? Good, 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 good. 1 over 4 factorial times 0.1 to the 4th. Okay, so let's go ahead and get that calculated. I'm going to go over here to Desmos and calculate. So we have, I'm not worried about absolute value. It should have absolute value around it. I think it's going to come out positive. So factorial times 0.1 to the 4th. Okay, so that's the error that I get when I do the calculation by polynomial versus plugging in. Okay, that's the value that they would want you to put on the AP test when they ask you to calculate Taylor's theorem or Lagrange error bound. Okay, it's for both sine and cosine, Gabby. Both sine and cosine. Okay. All right, I think there were like 5 zeros, so it was 0.0000. Let me double check that. 5 zeros, 416. 416. ... Okay, so this is the answer you're going to input when they're asking you for stuff today. Okay, let's take one moment and see how good of an estimate that was. Okay, so our actual error, remember, actual error, that's an A, is the absolute value of this. If I were to put sine of 0.1 in the calculator and I'm going to subtract the polynomial evaluated at 0.1, okay, which we have that number. So what says max? It literally means like there's a maximum, like a curve. When it says max, it means what is the biggest in that interval, right? Or for that value that number is ever going to get. What's the biggest possibility it could be? And for sine and cosine, we know it's never going to go above +1 or below -1, and we want absolute value. Did I clear it up, Gabby, or no? It might make more sense when we do the next one too.
Ms. Ballard?
Yep, go ahead, David.
Sorry, but where did the 0.1 come from again? Was that because I know this is on the sine wave.
It gave it to us in the problem. That's where we're supposed to be making our estimate at. Okay. All right. So I'm going to put this back into Desmos just to check it, and I'm going to kind of shortcut it because I don't want to run too long on time. I already know that that's the sine of 0.1, right? We put big parentheses around it. So that's our polynomial estimate, right? So I'm going to do sine of 0.1 minus that. So check that out. If I did, so I've got to go 8 decimal places. So we weren't too far off. Okay. It was, let me write that out, 8 decimals, see if it'll do. I don't know if it'll estimate any better than that. It won't. Okay, so let's see what happens. So it was 0. Oh, that's not what I want to write with. 0.1, 2, 3, 4, 5, 6, 7. And then it was, if I had used a rounded, it would have been 83331. So 83331. Dot, dot, dot. So we're not too far off. We could be probably a little bit better if we used a little bit more of a polynomial, but our error isn't that far off. It's got a lot of zeros in front. Okay, again, when you're looking at the error, you would probably, if you had that error and you're building a bridge, you would be in the tolerance probably of it. It would tolerate, your bridge would tolerate, and would probably still stand. How do I put in the p sub 3 of x? I'm not sure I know what you're asking. Gabby, can you help me? The back part? How do I put this in? I used this calculation that I had here. So all I did was I just put parentheses around what I had before, and I put sine of 0.1 in front of it. Okay. I cheated a little bit because I don't want to take a ton of time to do this. I still have one more to do, and I'm going way slower than I probably should with you guys on a Wednesday. So I don't want to totally lose you all. Okay, let's do 2. The good news is we're not doing 3. So this is going to be the last one we're going to do. You can cross 3 out. If you need the page for 3, you can use it. Okay. All right. So we're supposed to find the 3rd degree polynomial approximation for e to the x at x equals 1 centered at 0. So if we are centered at 0, does that mean we have a Taylor or Maclaurin? And you don't have to spell out the whole word. Just put Theorem. So do we have a Taylor or Maclaurin if we're centered at 0? Oh, some of you were brave and typed out the word. Nice. Technically, it's a Taylor, right? Because all Maclaurins are Taylors, but it is more specifically a Maclaurin. So we're going to use our Maclaurin stuff. The bad news on this one is, remember last time they were nice and I said, hey, look, they gave it to us. They didn't give it to us this time. So we actually have to calculate it. Eventually, we're going to get to the point where you see we have like some of these that we can memorize. This is one of them. We have a table. It somehow got cut out of yesterday's notes. So it is what it is. It's later on in your notes too. Okay, so I'm going to go with I'm going to create my table f and derivatives. Okay, so if I'm supposed to be going 3rd degree, writing a 3rd degree polynomial, how many derivatives do I need to take? Can you guys tell me that in the chat, please? How many derivatives do I need to take? All right, so 3. So I've got to go all the way to 3rd derivative. So my first one is e to the x. What's the derivative of e to the x, everybody? I'm waiting on everybody. I want to see everybody making sure we're in there. Okay, so it's e to the x. So luckily, all of those are e to the x. The c value is where we're centered. And I know that seemed kind of confusing because yesterday it said x equals, and today it's saying centering at 0. So we know the value we're going to plug in is the 1. So we get e to the 0. What's e to the 0, everybody? What's e to the 0? Put that in the chat for me. All right, it is equal to 1. So all of these are going to be 1s, aren't they? Because they're all going to be e to the 0s. So 1 is our coefficient. All right, we're going to write out our polynomial. So p sub 3 of x equals, which is really our estimate for e to the x, right? Or our approximation for it. All right, my first coefficient, just the way it is, plus my coefficient, x to the first over 1 factorial, plus my coefficient, that was my second derivative, right? X to the second divided by 2 factorial, plus my coefficient, x to the third divided by 3 factorial. All right, last time they told us that, hey, we're going to put in a 0.1. Okay, that's what we did. We had to estimate, figure out what the polynomial estimate is at 0.1. This time they're telling us figure out what the polynomial estimate is at 1. Okay, so I am trying to find e to the first is what they're wanting us to find, which is polynomial at 1. Okay, so I'm going to plug 1 into all this stuff. So 1 plus, this would be 1 over 1, basically, or just 1. 1 squared is 1, 2 factorial is 2. 3 cubed is 1, 3 factorial would be 6. Okay. When I add all of that up, let's see if I use 6. So 6 over 6 plus 6 over 6 plus 3 over 6 plus 6 over 6. I would end up with something like 16 sixths, not thirds, 16 sixths, which equals 8 thirds. Okay. So I know that E is about 8 thirds, estimated with a polynomial at 1. Okay. So the next thing we're supposed to do, notice the instructions were a little bit different. It says use Taylor's inequality to find a range of possible values. Before I can find the range, I need to figure out how good of an estimate that is. So I need to figure out the error. And then we will add and subtract the error from our estimate. So let's do the error next. So my error is my remainder at 3, because that's how far out they had me go. So I know I have to go 1 beyond. So what's 1 beyond? So what derivative am I looking at? Can you guys tell me that in the chat? What's 1 beyond? All right, still got 4 or 5 people listening. So I've got 4. The fourth derivative evaluated at, technically it's z. I keep writing x, don't I? It's a z. It's supposed to be a z. All right, over 4 factorial times x, or sorry, we're evaluating. What number am I supposed to plug in there? What are we evaluating at this time? Good, 1. Okay, perfect. All right, so now we've got to talk about that max value. So I'm going to do that out here in the left-hand column. Okay, so let's talk about it. We're got to find the max of e to the z, which is really, we're talking about e to the first. That's what we're trying to estimate here. So we need to know how big, what is the biggest we could estimate e to the first to be? We're familiar with e. We know e is a number. What is e? If we were to just find the decimal point for e, what is it approximately? All right, 2.57. That's a good guess. Oh, Lorenzo, nice. Is that your password? Or did we look it up? All right, it's 2.718, 2 point something, right? All right, 2 point something. It's a great password, isn't it? Because everybody knows pi, right? But nobody knows e. All right. All right, I only remember the first 3 too. 2.718. So I know that if I'm going to estimate this, though, I don't want to estimate it at 2.7. Couldn't I just go a little bit bigger? So where do you think I should estimate this at? I don't want a decimal estimate. That's too hard for my brain to calculate, right? There we go. We want to estimate at 3. We know it's not going to get bigger than 3. And it's okay if we go a little bit above where the estimate. We're talking decimal points here, tenths of decimal. We're okay to be a little bit above it, okay? So we are going to say that this is, or actually it's going to be an equal to here. It's going to be 3 times over 4 factorial times 1 to the 4th, right? Which is just 1. So I really have 3 over 3 to the 4th would be, or 4 factorial would be 24, which if I reduce that is 1/8. All right, so again, if they asked me for the error, I would use the 1/8 or the decimal equivalent. Okay, and I'm literally within like 2 lines here, guys. Okay. But they asked me for this range. So to get the range, what we're going to do is we're going to take these two values. So I'm going to take what we calculated as our estimate, right? And I'm going to subtract the error. Remember what we were trying to find was e to the first, and I'm going to add the error. If I hit my magical calculator button, right, and I wanted to look at that in the calculator, I got 2.541666666 repeating, okay? And then 2.791666666666. I can explain it in English again, yes. Would you rather I try to do it in Spanish or French? I couldn't do either one of those things. The equal sign being, no, your equal sign is fine. The approximate comes up here with the e there, and then we're equals after that. Okay. Go ahead, Natalie. I heard the thing blip, but I forgot that it meant question. What's your question? And then I've got to explain it in English again.
For when we were trying to like how you got 8 divided by 3, how did you get 16 divided by 6? I thought it would be.
How did I get 16 divided by 6?
Yeah, because 6 plus 6 is 12, and then 12 plus 3 is 15. 15 plus 6 is 21. So like.
What did I do?
You changed the 1/6 to 6 over 6.
I changed the 6 to 6 over 6.
The 1/6 at the end.
What did I do? I was copying their work, so that's what I was doing. So it should be 12, 13, 14. Is that right? Is it supposed to be 14 over 6? No. 12. No. This is 12. Oh, 3 over 6.
It was just the 1 over 6. Like you converted everything to 6 over 6 for the ones, and then you put 6 over 6.
Oh, duh. This is supposed to be a 1.
Yeah.
There you go. Now it's fixed. Now it should be 16, right?
Yeah. Okay. Thank you.
Okay. You're welcome. All right. I'm going to explain it in English. Okay. How far back do you want me to go, Gabby?
Just the inequality thing part.
The remainder?
Yeah.
Okay. So let me go back to the remainder. If you guys, if you've had it, we're done. We've looked at this long enough. You guys can leave. I will do the joke here in a few minutes once I explain it again, okay? Make sure you go work on the homework, okay? You still got like 10, 15 minutes of class left here. Make sure you work on the homework, okay? All right, so I'm going from here.
Wait, no.
So remember, what's wrong, Gabby?
I meant the range, sorry.
Oh, the range? Okay, so here?
Yeah.
Okay, so I'm going from there where my yellow is, okay? So to get the range, what I'm going to do is I'm going to take the estimate that we got with our polynomial, okay? So I'm taking the estimate we got with our polynomial, and I'm going to add and subtract the error. So it's the range, let me write it down. The range equal or implies the estimate from our polynomial, right? Which is really an estimate, right? And then add and subtract the